Alright, so bonding today. We have different types of bonds. So first thing, a chemical bond is the force that holds two or more atoms together. This chemical bond is that attraction, so it's that force that's pulling them and holding them together. The number of valence electrons possessed by an atom determines the way it bonds with other atoms. So here is where you're going to need to become very familiar with how to find valence electrons. I've already shown you ways on how to find the valence electrons in the S and P sublevels, basically in family groups 1, 2, and then 13 through 18. With your transition metals, those are found, and as well as your lanthanides and actinides. You can essentially write out your electron configuration and then figure it out by looking at your highest energy level of your last S&P sublevel or your last S&P orbitals and adding those together. So atoms usually form bonds to reach a stable state, with the exception of noble gases, which are already stable in nature. So one of the questions that were on your test last week was what makes something stable? So when you answered that question on the test, how did you know it was stable? What makes something stable? It is a full outer shell of how many? 8 valence electrons, right? That is a full outer shell. That's what makes it stable. Noble gases are already stable because why? They already have 8. They don't need to have any. They don't need to bond with anything.
Is this one plan?
All right. So.
Never mind.
All right, so the next part of this and what we're going to be spending time on for today's assignment are electron dot structures. So these structures are where we represent electrons with dots. Instead of using the arrows like we did with orbital diagrams, now we're moving into these electron dot structures or Lewis dot structures. And this is where you'll find that electron dot structures are types of diagrams used to keep track of valence electrons and are especially helpful when used to illustrate the formation of chemical bonds. In the coming notes that we're going to do tomorrow and then for the rest or almost the rest of this unit, but you're going to hear me talk about bonding sites. So when I talk about a bonding site, these Lewis structures are going to help you. When we place these electrons, these electron dot structures are going to help you determine bonding sites. Okay.
Wait, so is it the same as like having the neutrons and protons in the little circle and then like 2 dots and then
that was to represent all of the electrons. This is just representing the valence electrons. And I'm going to show you on the next slide. So here, this is where I'm just adding this table. So underneath, on your notes, you're going to find this table right here. So in family group 1, the element that I'm giving you here is lithium. So lithium has how many valence electrons?
1.
1 valence electron. So the way that we represent these are we're going to draw them around. All the valence electrons are drawn around. So when we do these, so you have element, whatever it is, start 1, 2, 3, 4, 5, 6, 7, 8.
That's the bonders.
About the dots, does it matter? Does it always have to start with 2 on the top, or could it be like just 2 in any area? Like, does it matter?
You need to place them just like this. So 1, 2, 3, 4, all the way around. So you go clockwise, give each side 1, and then go back and pair it.
Like the corners.
On the,
Mine had order.
when it goes to on 5 for nitrogen, it says it's on top.
Okay, so I haven't gotten to nitrogen yet. I've gotten to just 1 valence electron. Nitrogen has 5. So when I get to those, I'll explain those. But how Lewis dot structures are arranged is that you can start them in any order. So like I chose to start here. This is how I'm teaching you guys. So on the test or the quiz, they're going to start here. The book does it a different way. The book starts up here. Okay, that's where this table is from. It's an image from the book. So you'll find that, let's say if we did nitrogen, so nitrogen is here. How many valence electrons are in nitrogen? 5. So to place them, if we started here like the book does, 1, 2, 3, 4, 5. If we started where I started right here, 1, 2, 3, 4, 5. It's essentially the same thing. It's just where you start needs to be where you start going around the entire time. You can make sure that you know that you have to fill up each side first before you go back and pair it. So what is that similar to in the rules that we just went over for the orbital diagrams?
No, Pauli exclusion.
You had it right?
Oh, Hund's rule.
The Hund's rule. The Hund's rule says with orbital diagrams you had to fill them all with an up arrow before you go back and fill them with a down arrow. Similarly, we're not using arrows, but on this one you have to fill all the sides first with an electron dot before you can go back and pair it.
Wait, so when you go back and pair, where do you start again? Like,
Same place that you started before. So like on this one I started here, so I'll do 1, 2, 3, 4 all the way around, and then start here again.
oh, okay.
Okay, so just like I did here, I started here on this side, 1, 2, 3, 4, and then I paired it up here. Yeah.
So you can start anywhere.
Yes, but don't start anywhere. I would recommend not starting anywhere beyond these two. Just to make sure that we're all on the same page here. And again, like I'm showing you in here, when I show you here, that order up there, this one right here, is what you'll see on the test. Okay? So there's different types of bonds. First one is an ionic bond. So we said before when I asked you that in an ionic bond, electrons are transferred between 2 atoms. Okay? In a covalent bond, these electrons are shared. When 2 atoms combine, the number of electrons transferred or shared is generally the quantity needed to satisfy the octet rule. So the first thing that I told you you'll hear me talk about quite a few times in this chapter is bonding sites. The second thing you're going to hear me say a lot is the octet rule. You'll hear me ask a lot of questions. Does this satisfy the octet rule? Well, what does octet mean? Anybody? What number does octet mean?
8.
8. So it satisfies the 8 rule, meaning you need 8 valence electrons. So anytime that something is bonded together, it's got to satisfy that octet rule. Okay? The only exceptions, written down here, the only exceptions are hydrogen and helium. Okay? Just remember those two as being the only exceptions.
Did you make this PowerPoint?
You don't like it?
I know there's grammar errors.
Yeah, this is for more probability.
Or more stable.
Allowing for more stability, yeah.
So what if does it ever pass 8 electrons?
8 valence electrons is the max that you'll go. Because if you think about it, the valence electrons are the amount of electrons in the highest energy level of your greater S and P orbitals. Well, S holds a maximum of how many electrons?
1. No.
S has 1 orbital which holds 2 electrons. So a maximum of 2 in S, and P holds 3 orbitals, a maximum of 2 in each, so that is, so 6 and 2, 8.
So why is it only S and P?
Those are typically your outer shells. Good on this?
Yes.
Yes.
1 second. Okay. Alright. So next one. Here we have where I told you ionic compounds are formed when a metal and a non-metal bond. So remember, ionic is metal and non-metal. So on your periodic table, last week we shaded in all the different types of elements. So including hydrogen, all of your nonmetals are predominantly here, well right here, and then hydrogen's included. The majority of your periodic table consists of what?
Non-metals.
Metals, right. So you've got a bunch of metals here. You've got the alkaline, you have the alkaline earth metals, the transition metals, all the way over here. What are these right here? Your staircase elements are metalloids.
Okay.
And then here are your nonmetals, and then the last row is your noble gases. Typically, like I said before, noble gases won't bond with anything because they're already satisfied. They already satisfy what rule?
Octet.
The octet rule. Okay. The next one. So more about ionic compounds. So metals become cations, which are positive ions, and your nonmetals become anions. What holds these together are these electrostatic forces. That's holding the bonds together, holding them in place. General properties of an ionic compound exist as a solid crystalline in structure, which you can see right there. They have high melting and boiling points, and then they conduct electricity when dissolved in water. So if you think, going along with these two right here, one of the most famous ones that everybody knows about is NaCl, which is table salt. So the chemical name for it is sodium chloride. Well, sodium is your positively charged, and chlorine is your negatively charged. That one is your cation, and this one is your anion. So positive and negative. Whenever you write compounds, your positive one is written first. Your positive element is written first.
What do I write for the last one?
It says that ionic bonds are split.
The ionic bonds on the bottom was a little bit of a typo. I would just write down those three on the last line.
So general properties.
Yeah, the properties on the last line.
Oh. Okay. Can I write that down?
So again, properties, they exist as a solid crystalline in structure, have high melting and boiling points, and then they conduct electricity when dissolved in water.
You just write it on
Just right on the bottom. The ionic bonds at the bottom, that was a typo.
So these are general properties for ionic.
For ionic compounds, yeah. All right. So on the next slide, as you guys are finishing writing that one up, if you haven't already gotten out your periodic table, go ahead and do that. We just need to make sure that we all have our charges written. And here are your charges. So what is this called right here, this column?
The alkaline.
The alkaline metal. So this is called, going top to bottom, is
One.
group 1,
Group 1.
right? And that is a positive 1 charge. Family group 2 are your alkaline earth metals, and those are that's a positive 2 charge. Skip over your transition elements, your charges, I'll show you how to solve for those later on. But then you get into family group 13 here, and that is a positive 3 charge. Here, family group 14, those you'll find have 4 valence electrons. So there could be no charge, but I would just write on the top a plus or minus 4. The next one right here, so think about it in a way where you build up to a positive 3. So you have positive 1, positive 2, positive 3. We're here at 0, or plus or minus 4. Now we got to go back down. So we're going to go negative 3 here, negative 2 here, negative 1 with your halogens, and then 0 is for your noble gases. Those don't have a charge.
And these are, what would I exactly label? Ionic? Ionic
These
charge?
call them their charges, or they're also referred to as oxidation numbers. Alright, so we talked about ionic, so here's some covalent information. So covalent compounds form when 2 or more nonmetals bond. So an ionic compound is a metal and a nonmetal. A covalent compound is when it's 2 nonmetals. They can be polar or nonpolar, meaning all that polar means in this one is that electrons are shared unequally. It's kind of a little bit off. So the same amount of electrons with your cation is not being shared at the same amount as your anion. So in this case, you got hydrogen and chlorine. Hydrogen we know to be the exception to the octet rule. The exception meaning that hydrogen and helium need how many?
2.
2. 2 to be satisfied. So here you have 1, and then you have chlorine here with how many valence electrons?
7.
7. So pulling them together, hydrogen and chlorine are 2 nonmetals. So with 2 nonmetals, you're going to form what type of bond?
Covalent.
A covalent bond.
So
So
they're sharing.
pulling them together, they're going to now share these electrons. That's why you'll see it here. So you've got hydrogen being satisfied here with the 2, and then over here is chlorine. It's got 2 here that is being shared, 4, 6, and 8. So each rule is satisfied. You have, it's satisfying here, the octet rule, because hydrogen is the exception to 8. So it can be satisfied with 2. And then chlorine is being satisfied because it's got all 8 around here. And they're sharing. So being that it's sharing electrons, it is a covalent bond.
Oh, it's right here.
There's a little bit of a diagram.
Oh.
I have a question.
Yes.
Can 2 metals bond?
Alright, so in non-polar covalent bonds, so we said a polar one was where electrons are shared what?
Equally.
Unequally.
Unequally.
So in a non-polar, electrons are shared
Equally.
equally. Okay? With electrons being shared equally, this often occurs when 2 atoms of the same element are bonded together. So you've got an atom of hydrogen and another atom of hydrogen. Being bonded together, that's what you see here. So you've got 1 valence electron, 1 valence electron. Here they're bonded together to make a hydrogen molecule. Also what's known that we talked about before, a diatomic hydrogen molecule. Okay? Same thing with fluorine, 2 of the same. They both have 7 valence electrons. Pulling them together, bonding them, that's where you'll get the fluorine molecule. Again, diatomic. Fluorine is diatomic. And then just some information about covalent compounds.
You write that down?
Yeah, just right on the bottom.
Okay.
So general properties. Covalent compounds exist as gases, liquids, or solids. They have low melting or boiling points. They are poor electrical conductors in any or all phases that they're in. And then large organic molecules such as carbohydrates or proteins are covalent compounds. Alright, so as you finish that up, there's a video to watch that I'm going to have you guys watch separately from this. Go ahead and switch over to the worksheet that you guys got today for the Lewis structures. Got it?
Got it.
Alright.
Wait, it's gonna Go back. Oh, somewhere.
Of course, Dina is so cute. Dina is absolutely the sweetest girl. She's so like happy all the time. Even when she's sad, she's so happy. It's so I remember like the day she got back after like a dog bit her or something. Like she's like kind of down. But now what's wrong?
Wait,
She's
just
so
like
nice.
videos?
What?
The Vicks,
Publix.
the ones that have Vicks in it.
We're supposed to watch the,
Look at her like 7 blocks.
Yeah, afterwards.
after we do this?
Yeah, we're gonna do this first.
Are we doing
Yeah.
this as a group?
Is it individual watching the video?
Yeah. So the worksheet that you guys have, I'm gonna show you one. So let's take a look at that worksheet real quick. All right. So complete the following chart for the using Lewis dot notation. So the first one that I wanted to do with you, let's look at xenon. So we know xenon to be what type of element? It is a noble gas, so that tells us how many electrons? 8. So we place them, we know that it's going to satisfy and fill up everything, but let's place them correctly.
Wait, that has 8 valence electrons?
Right. So you're going to have 1, 2, 3, 4. Just go clockwise. So wherever you start, continue to go clockwise. 5, 6, 7, 8. So you're just placing those dots around.
So like, how do you know how many?
I want you to get used to making sure, if you're good, if you know how to do it, then however you want to do it. But you're not always going to fill them up. So the next one, let's do fluorine. Fluorine has how many?
7.
7. So we place those. So 1, 2, 3, 4, 5, 6, and 7. All it is just picking a starting point. So we'll do,
Doesn't matter where you start.
Can you do a little bit slower?
let's do boron right here. How many for boron?
Boron is 3.
Boron is how many valence electrons?
3.
3. So right here, Riley, start here. Do you want to start on the left? Do you want to start on top? I teach you guys, I want you guys to start on the left. So if you start on the left, start 1, and how many do we need?
2 more after that.
We need 3 total. So you're just going to place them on each side of the symbol. So you fill up, you have to fill up all the sides before you can go back and pair it. So you have 1 there, 2, 3. We'll do another quick one. Where was it? Krypton, right here. Krypton is what type of element? It's a noble gas, so it tells us how many electrons? 8. So again, we place them. So start on the left. So krypton here starts with 1. Top, right, bottom, left, top, right, bottom.
So it's kind of like the thing, like the arrows. You have to fill them all in around first. And
Exactly.
Then you go back and fill.
You fill all the sides first with 1 dot, and then you go back and fill it with the second dot.
That was a good metaphor, right?
Huh?
So hydrogen's
Just 1 dot. That's it.
So hydrogen has 1,
Mm-hmm.
the Be has 2,
Mm-hmm.
and then you just don't like.
Don't do your transition metals.
So then boron has 3.
Mm-hmm.
Okay.
4, 5, 6, 7, 8.
Are you gonna do one of these with the?
Yeah.
Can you explain that?
Alright, so that's how we're going to do that one. Now let's look underneath at the table. So this one says, I'm giving you group A, and I'm telling you in group A, there's how many valence electrons?
1.
Element X, any element in group A is represented by 1 valence electron. So first tell me what elements have 1 valence electron.
Hydrogen, lithium, sodium, potassium. Okay, just keep.
Hydrogen, lithium, looking on which group are you looking at?
First one.
Which is called your
Alkaline metals.
alkaline metals. So hydrogen, lithium, sodium.
Rubidium.
Potassium.
Potassium,
Rubidium.
rubidium,
How do you pronounce that?
cesium,
Okay.
Francium.
and
How
francium.
do you pronounce the RB?
Rubidium.
Rubidium.
All right, so now you've written all of the elements that correspond to one valence electron. So now this number of electrons lost or gained. First tell me how many valence electrons are in this category?
One.
There's one. So ask yourself the simple question, is it easier to lose one or to gain 7?
Lose one.
So you're going to write 1 lost.
Oh.
When did you negative?
What if it's like 3 or 4?
Huh?
What
If it's like 3 or 4?
yeah.
Yeah, how do you
Can we
know
write run?
that?
It would be
We'll get
easier.
into that.
Okay, sorry.
Oh, I guess.
All right, so the charge or the oxidation number for everything in group A
Plus one.
is a +1.
Knew it.
That's because we're losing that one electron. By losing that electron, you're now becoming a positively charged ion. So if hydrogen has 1 valence electron, if it bonded with chlorine, which has 7, like that, if it bonded with chlorine, it's going to go essentially right there, and this is going to make 1 bond. So it's now, when it loses that electron, it becomes a positively charged ion. So that's all that this was meaning, that I wanted to show you, is that when you lose one, you become a positively charged ion. Okay, so the loss of an electron makes you a positive charge. So we'll do, let's say this one, for element X that has, any group, in this group, any element X has 3 valence electrons. So what group, or what elements are in that group, I should say?
Boron.
Boron.
AlGaIn.
So you have boron.
Aluminum.
So all of those in that category, boron, aluminum,
Gallium.
gallium,
Indium.
Gallium.
and what's that last one? TM.
Yeah.
Okay, so now we've written all of them in that category that have 3 valence electrons. Now here it's asking you, well, okay, there's 3 valence electrons. Is it easier to satisfy the octet rule? Is it easier to lose 3 or to gain 5? To lose 3. So you're just going to write 3 lost. And then the charge is a +3. So this plus right here tells you that you're losing electrons. That's what this plus means. The number tells you how many you're losing.
I have a question about the next one.
Okay.
Can I go ahead and say it?
On
Okay,
this
well,
one?
yeah, because we wrote down the charges, but like, there's not one.
Right. So when we get into this one, first of all, what elements in group D represented with 4 valence electrons are in that group?
Carbon, silicon, germanium.
So just looking at that group, carbon, silicon,
Germanium, tin, SN, BB,
and lead,
yeah,
and
and then
this.
Sclerovium.
UUQ.
UUP.
UUQ.
Oh no.
No.
So after lead, it's done. We're not going to do any of the undiscovered elements yet.
Oh,
So it stops at lead. So this is asking you, okay, well, first of all, we have 4 valence electrons. Is it easier to lose 4 or to gain 4 to get that octet rule satisfied?
there's no. You could go either
You can
way.
kind of go either way. So what I'm going to tell you here is that it's not really essentially the loss or gaining of electrons. We're not going to lose or gain an electron. In this column, well, in that column, I was about to show you a periodic table up here. In that column that has all of these elements, you're not going to gain or lose. You're going to share electrons. So not gained or lost. But shared.
So what would you put for the oxidation number?
So the oxidation, so pretty much there could be none, or you can put in there what I've been telling my classes is a plus or minus 4. So you could have a positive or a negative charge on that.
So that could be negative or.
Yeah.
So how, like, what would make it?
There won't be examples today, but we'll go into examples. I'll show you how to do those. The only thing that we didn't do this one, but with 2 valence electrons, when you write down what's in the alkaline earth metals, don't forget to add what element. What element was an exception that has 2 valence electrons? Helium. So helium would be the first one that you write here, and then all the other ones. Any other questions?
Nope.